The second type of word problem that we're going to encounter on our exam in May are called optimization word problems, meaning to optimize, where things are at their highest or things are at their lowest. We also call these max-min word problems. Remember that I have said before that calculus is the first mathematics that we've encountered that models the real world extremely well. Through extreme values, maxima and minima, we explore ways to do something at its best or its extreme, either high or low. For instance, a farmer would want to choose a mix of crops that would yield him the highest profit. A doctor might want the smallest amount of a drug to produce the desired effect. A manufacturer always strives to minimize cost and maximize profit. All of these real-world situations can be expressed mathematically as a function, and we can use the powerful tool of calculus to find the helpful optimization values. Let's remember, when we're dealing with max-mins, they can happen anywhere on an interval. They most especially could happen at an endpoint. I find that when we do word problems, students don't have any trouble looking for where the derivative equals 0, or maybe even where the derivative does not exist. Remember those stationary points and singular points. But the one critical point that students repeatedly forget to check are the endpoints. So make sure that you remember maximums and minimums can happen anywhere on an interval. And if we are on a closed interval, you must check the endpoints because your extreme value could happen there. The max-min existence theorem is something we've kind of been dancing around as far as maximums and minimums are concerned, but I will formally give it to you. It's something we intuitively have discovered, but here it is formally. If a function is continuous on a closed interval, both endpoints must be included in the interval, then we are guaranteed by this theorem that f attains both a maximum value and a minimum value somewhere on that interval. It doesn't necessarily have to be at an endpoint, as we saw in the graph a while ago, but it could be. This theorem guarantees us of both a max and a min on the closed interval. I also want to just interject that, remember, the max means global or absolute. The min means global or absolute. When we have these word problems, we're looking for absolute extreme values. We are going to explore all locals and endpoints. Remember, endpoints are not candidates for locals, but we're going to explore all locals and then do some comparing and find the extreme value, either the maximum or the minimum, based on what the words are telling us to do. Please remember, you have three types of critical points. Stationary points, where your derivative equals 0. Stationary points, where your derivative does not exist because you have some sort of discontinuity. And singular points, where your function has a cusp, which is also where your derivative will not exist. And endpoints. This is a half open, half closed interval. We are not guaranteed of both a maximum and a minimum on this function because we do not have a closed interval. Looking at the graph of this function does indeed have a minimum. The minimum on this function appears to be -2. But this function does not have a maximum because as inputs approach +4 from the left, Outputs, yes, are approaching what appears to be positive 4, but because of the hole here at the end of the graph, they never get to 4. We can't say that the maximum is any real number value, because how many ever 9s you give me after that decimal point, I can always give you one more. There are infinitely many points. Remember the density of the real number line, and this is why on an open interval we might not be guaranteed an extreme value. Just things to consider. Now let's work some examples just like we did for related rates. There is a process. It is a different process than the process we used in related rates, but we are going to read the problem. We are still going to model what the words are telling us. We are still going to use excellent notation and labels, but we are not going to differentiate with respect to time. So this process is different from what we did with related rates. So the optimization process looks like this. We're going to read the problem, then we're going to draw a picture and label it. Build a rectangular pen with 3 parallel partitions using 500 feet of fencing. What dimensions will maximize the total area of the pen? I have a rectangular pen. That's those words. With 3 parallel partitions. 1, 2, 3. Those partitions are parallel. I'm going to use 500 feet of fencing. So as far as fencing is concerned, I have 500 feet. What dimensions will maximize the total area? I want max area. That's what I'm after. So I'm going to draw a picture. I'm going to label my picture extremely well. I think I better draw my picture a little better. Now I'm going to call the horizontal distance here x. I have 2 of those. I'm going to call the vertical distance y, and I have 1, 2, 3, 4, 5 of those. That's the fencing that I'm going to use. So how could I maximize the area? The area, by the way, is going to be found by length times width. So I know that. How can I use 500 feet of fencing? Well, isn't that perimeter of all of those rectangles? If I add them together, isn't the perimeter, which is 2x lengths plus 5y lengths, doesn't that have to be 500 feet? So I want you to notice something. We're trying to develop a process for answering max-min word problems. I have 2 equations. One of which they ask me to optimize. It's the optimization or max min equation. The other one gives me a relationship between all my variables. This is the relationship equation. And here's how the process is different from related rates. I'm going to use the relationship equation. Use the relationship equation to put the optimization equation in terms of only one variable. I want to optimize and find the max area. But what I want to do is I want to differentiate, because I'm going to use the derivative, set it equal to 0, see where it's undefined. I want an area function in one and only one variable. And then I am going to differentiate with respect to that variable. I'm not differentiating with respect to time. So I want to use the relationship equation to put y in terms of x. I like taking derivatives with respect to x. So I want to be able to put this factor in terms of x. So I'm going to take the relationship equation and solve it for y. I'll have y equals some expression in x. And then everywhere in the optimization function that I see this variable, I can write this instead. Remember, that's what equals allows me to do. So let's go back down here. I want the area function completely and totally in terms of x. So I'm going to take my relationship function p, and I'm going to solve that for y. I'm going to subtract 2x from both sides, going to divide both sides by 5. So everywhere that I see a y in the optimization function, I get to write this instead. This is equivalent to x times y. Now I have a function totally and completely in terms of one variable. The next step in the process is to maximize that function. So I'm going to clean this up a little bit. I'm going to distribute that x to make my derivative easier. So a prime of x is 100 minus 4/5 x. I need to know where that equals 0. This is my derivative function. I'm hunting critical points. Going to use the first derivative test to see where I have a max or a min. Just like I did for functions that I graph, I just happen to be in a word problem here. So I'm going to find critical points. That's what I'm doing here. This is a well-defined function. I don't have to worry about values of the derivative that do not exist. So I'm going to add this term to both sides, but I'm going to write that term first. Hopefully you can go here with me. I'm going to multiply both sides by 5/4. That's 500 divided by 4. That cleans up to 125?